I'm a professional geologist, but I always seem to forget that chalk is a type of sedimentary rock. That's right, your everyday run-of-the-mill chalk is a special type of limestone, a sort of carbonate rock. I'm not entirely embarrassed that I forget it. After all, chalk is a really strange and unusual rock when you really think about it. The grains of this rock literally rub off when you press it to a surface. How odd is that? What other rocks do that? But you know what is really strange? Ancient Egyptians built the Great Pyramids of Giza out of limestone, and they've survived over 4,000 years thus far. Clearly, the Great Pyramids aren't made of the same sort of limestone. In this context, what makes one limestone different from another? What exactly does it consist of? Let's start from the beginning. By definition, a limestone is a sedimentary rock that consists mostly or entirely of calcium carbonate. This calcium carbonate may be present in one of two mineral forms, aragonite or calcite. Generally speaking, calcite is usually more common, particularly for limestones that are ancient. Calcite usually makes up 50% of a limestone or more. Calcite is just one of many minerals in the carbonate mineral family. Some of the other important minerals in this group include aragonite, siderite, and dolomite. Problematically, calcite and aragonite have the same chemical formula. They both consist of calcium carbonate and are identical in composition. Although calcite and aragonite are identical in composition, they have different crystal lattice structures. This is important, as it affects not just their observable properties, but also their stability. Aragonite is considerably less stable than calcite, and over geologic time, we often see that aragonite naturally becomes calcite. Siderite has a different composition than calcite. It consists of iron carbonate. But siderite has the same crystal lattice structure as calcite. As a result, it can be very difficult to distinguish calcite from siderite and vice versa, based on appearance alone. A chemical analysis or reaction of some kind is typically required. Dolomite has a different chemical composition and crystal lattice structure than calcite. It consists of calcium, magnesium, and carbonate. However, dolomite occurs as a sedimentary rock called dolostone. A dolostone is a rock that consists mostly or entirely of the mineral dolomite. Limestones and dolostones are both considered carbonate rocks and have fairly similar properties, making them difficult to distinguish. Luckily, neither aragonite nor siderite make up similar rocks. Fortunately, there is an easy way to distinguish calcite and aragonite from dolomite and siderite. We can also use this method to distinguish between limestones and dolostones. To identify and distinguish these minerals and rocks, geologists employ what is called the acid test. This test is simple. Simply drop a little hydrochloric acid on a sample. If the sample fizzes, then it means there was a reaction that produced a gas, carbon dioxide. Therefore, the sample must contain calcite aragonite, or dolomite. If the sample is a rock, therefore, it must be a limestone or a dolostone. You can usually go one step further for rocks as well. Limestone tends to be more reactive on the surface than dolostone. So if there's a lot of fizzing, then you can conclude that the rock is probably limestone. If there is no fizzing whatsoever, you can conclude that the mineral is siderite or something else entirely. Let's focus back on the rocks now. When it comes to the rocks, most dolostones are created from limestones through a process called dolomitization. Dolomitization is a complex process that occurs under a variety of conditions. It generally happens when the calcite in limestone is exposed to a fluid with high concentrations of magnesium and low concentrations of calcium. This causes mineral alteration of calcite, leading to the formation of dolomite. So overall, for this discussion of carbonate rocks, we're going to concentrate on limestone, given that it is usually the source of dolostone. Limestones consist of sediment from various sources. Many limestones contain large grains and particles called clasts. Some of these clasts are lithic fragments derived from weathering and erosion of pre-existing carbonate rocks. We refer to these lithic fragments as lithoclasts, and they are usually greater than 2 millimeters across. In the grand scheme of things, however, lithoclasts are not very common components of limestones. You never find limestones comprised entirely of lithoclasts. Bioclasts, on the other hand, are far more important. Bioclasts are particles, grains, or pieces of organisms, such as fragments of shells. Put another way, bioclasts are biogenous sediment. Bioclasts come from a variety of sources. Seashells, which are made of calcite and aragonite, are common grains in clastic limestones. Some of the most common bioclasts that you are likely to encounter in limestones come from mollusks that live in the ocean, like bivalves or clams, marine gastropods or snails, and cephalopods, which include relatives of squid and octopi that have shells. These mollusks all tend to produce hard shells made of aragonite, which can become calcite in limestone over time. Other ocean animals produce shells made of calcite. These animals include barnacles, encrusting moss-like animals called bryozoans, sea urchins, sea stars, and sand dollars, and other animals that we collectively call echinoderms, and another group of bivalved shelled animals called brachiopods. And of course, coral. Coral are heavy biomineralizers. They build absolutely massive reefs made of calcium carbonate. They generate a lot of bioclasts. But it's not just animals. Plants, algae, and microscopic organisms produce bioclasts as well. These include a group of red algae known as coralline algae, various species of green algae like Halimeda here, and various microorganisms like foraminiferans and coccolithophores. Besides bioclasts, limestones can contain other types of grains as well. Some limestones contain lithic fragments called intraclasts. Intraclasts are irregularly shaped grains that form from erosion of partially lithified sediment. A specific example of intraclasts are rip-up clasts. Rip-up clasts are gravel-sized pieces of clay or mud that are created when an erosional event removes pieces of clay-rich sediment and transports them some distance. Because clay particles stick together and are cohesive, the pieces can be transported and subsequently preserved when they are finally deposited in place. To understand this, picture a depositional environment where layers of mud are being deposited. Over time, these layers will be lithified through compaction and cementation. But before the sediment becomes solid rock, a flow could come and cause erosion, ripping up some of the material and transporting grains of this material to a new location, where they will get redeposited in a new layer of sediment. We call these grains intraclasts. Beyond bioclasts and intraclasts, limestones contain a variety of other grains as well. Take, for example, these spheroidal grains consisting of calcium carbonate. If they are less than 2 millimeters in diameter, we call them ooids. And if they are on the larger side and are more than 2 millimeters across, we call them piezoids. Ooids and piezoids have a distinct appearance. Typically, each one is a near perfect sphere or ellipsoid made of calcite or aragonite. If enough of them accumulate in a depositional environment, they produce a distinctive type of clastic rock called oolitic limestone. It is not unusual to find oolitic limestones where nearly every grain is an ooid. If you cut open one of these ooids, or make a petrographic thin section from oolitic limestone like this, you can see that each ooid resembles a tiny concretion. Each ooid consists of rings or layers of calcium carbonate surrounding a central nucleus. In some cases, the nucleus is simply a particle of sediment, but in other cases, the nucleus is a bioclast. Here, you can see an ooid where the nucleus is the shell of a microorganism called a foraminifer. Evidently, a chemical reaction caused calcium carbonate to precipitate layer after layer after layer surrounding the foraminifer shell until it was entirely encased inside of the ooid. In this sense, ooids and piezoids represent a type of hydrogenous sediment. So what causes an ooid or piezoid to form? It is a matter of some debate exactly what causes these things to form. That said, depositional environments where you can find ooids tend to have warm, shallow waters with high concentrations of dissolved carbonate, waves, and the presence of bacteria and other microbial organisms that cause calcium carbonate to precipitate out of seawater. It is thought that the waves agitate and circulate water, helping to supply calcium carbonate to the bacteria and ooids growing in sediment located beneath the surface of the water. In this context, oolitic limestone is thought to be a very good indication that a wave-dominated depositional environment existed in the past. Of course, not all round grains in limestones are ooids or piezoids. Another important group of carbonate grains are called peloids. They do not have any concentric layered structure, and they are usually less than 1 millimeter across. For these reasons, Peloids can be hard to recognize, and they don't have any distinguishing characteristics. Even so, peloids have a much simpler origin than ooids and pisoids. Most peloids are remnants of fecal pellets that were produced by ocean animals like marine snails. Unfortunately, peloids are more common than you might expect, but thankfully they now consist of calcium carbonate. In any case, in the real world, things can get a little more complicated than simply ooids, pisoids, and peloids. Calcite also precipitates as a cement during lithification of carbonate rock. As a result, it can form between grains and bind them together as aggregate grains. When all of the grains are spheres, we call them grapestones. To see the final component of carbonate rock, we must look past the big pisoids, ooids, and peloids, and past the bioclasts and intraclasts. In many limestones, these large clasts are surrounded by fine-grained material called lime mud. It is also known as carbonate mud, but I suggest you remember it as micrite. Micrite is the brown-gray material in between the clasts in this image. Micrite consists of particles of calcium carbonate that are less than 4 micrometers in diameter. Micrite grains are tiny. Micrite particles form through a variety of pathways. Some micrite represents hydrogenous sediment that forms from chemical precipitation of calcium carbonate in water. Other micrite particles form from the breakdown of bioclasts, intraclasts, ooids, and other large grains. We call this process micritization. It is the breakdown of clasts into micrite. Here, you can see a large clast surrounded by a micritic envelope. It is in the process of being broken down into micrite. You now know all of the types of sediment and carbonate rocks and how they originate. And you will soon learn to use this knowledge to classify limestones into different categories. But before we attempt to classify limestones, let's return to the topic of chalk. Why is chalk, well, chalky? Why is it such a good writing utensil? Chalk is very much a limestone. It reacts with acid. It consists of calcium carbonate. Some of the most spectacular and famous chalk deposits in the world are located on the southeastern coast of England, across the English Channel from France. You've probably heard of these cliffs before. They're called the White Cliffs of Dover, and they're breathtaking. How did this beautiful limestone come to be? The grains in the White Cliffs of Dover consist of tiny shells of microscopic algae called coccolithophores. This electron microscope image shows you the sizes of these shells. Each one is only a few micrometers across. They are incredibly small. Not to mention, each individual coccolithophore shell is a sphere that easily breaks apart into many smaller plates. Each plate here is less than 1 micron in size. Coccolithophores are commonly called nanoplankton because their bodies consist of nanoscopic plates. So why does chalk produce dust? And why can we use this dust for writing on smooth surfaces? It is because chalk consists of clay-sized pieces of nanoscopic algae. With this in mind, when your professor calls you up to answer a question on the board, just remember, nanoscopic algae, which lived millions of years ago, are actually the ones to blame.